Jake Morrison wiped sweat from his forehead as he looked across the massive gap in front of him. The morning sun on planet Kepler 442b was hotter than Earth's sun, and the air felt thick in his lungs. He had been at the Galactic Engineering Academy for 6 months now and thought he was getting used to alien worlds, but this ravine was something else entirely. The Kethmaran ravine stretched 200 meters from one side to the other. Jake could barely see the bottom through the morning mist. Sharp rocks jutted up from the depths like broken teeth. One wrong step and anything that fell would be smashed to pieces 500 meters below. "This is impossible," said Zeftar, his crystalline body catching the sunlight and throwing rainbow patterns across the ground. The alien's voice sounded like wind chimes in a gentle breeze. "My calculations show that crossing this ravine with our current resources has a success probability of 0.03%. Jake's teammate Quinn Dal floated nearby in his environmental suit, his gaseous form swirling with what Jake had learned was frustration. "The atmospheric conditions are all wrong," Quinn Dal said through his suit's speakers. "Wind shear patterns make any aerial approach extremely dangerous. We would need perfect weather conditions that occur perhaps once in a standard year." Velnara scuttled closer to the edge on her 6 spider-like legs. Her multiple arms moved independently as she took measurements with different tools. "The cliff faces are unstable," she announced in her clicking voice. "Any anchor points would need to be placed at least 50 meters back from the edge to have adequate holding strength. That would require a span of 300 meters, not 200. The largest member of their team, Throckman, stood like a living mountain of gray stone. His people were known for their strength and their careful thinking. "We should find a way around," he rumbled in his deep voice. "My geological scans show the ravine ends approximately 200 kilometers to the north. We could reach the research station in perhaps 60 standard days." Jake listened to his teammates argue while he studied the problem with human eyes. Professor Hixandros had given them this assignment 3 days ago. They needed to transport delicate seismic monitoring equipment worth millions of credits across this ravine to the research station on the other side. The equipment would help predict earthquakes that could destroy 3 major cities and kill thousands of people. The professor had made it clear this was not just a school project. Real lives depended on getting the equipment across safely and quickly. The current earthquake prediction models showed dangerous activity building up. They had maybe 2 weeks before the situation became critical. Jake watched his alien classmates continue their debate. Each species approached problems in their own way. The crystallines, like Zeftar, thought in pure mathematics and logic. They needed perfect calculations before they would attempt anything. The nebulites, like Quindal, understood air and atmosphere better than anyone, but they wanted to study every wind pattern for months before making a decision. The arachnoids, like Velnara, were master builders. They could create structures that lasted for thousands of years, but they needed the right materials and lots of time to do things properly. The granite-born, like Throckmen, were incredibly strong and tough, but they believed in taking the safest path even if it took much longer. Jake understood why each of his teammates thought their way was best. The problem was that none of their ways would work fast enough. While they spent weeks or months planning and calculating, people would die in those 3 cities. He walked along the edge of the ravine, looking for something his teammates might have missed. The cliff face was mostly solid rock with some cracks and ledges. A few tough plants grew in the crevices. About a kilometer upstream, the ravine was wider but had some interesting rock formations. Downstream, it got narrower in places. "Jake," called Velnara, "what do you think of my preliminary bridge calculations?" Jake looked at the complex diagram she had drawn in the dirt with one of her arms. The design was beautiful and would probably last 1,000 years. It would also require materials they did not have and a construction crew of hundreds of workers. "It looks very strong," Jake said carefully. "How long would it take to build?" "With proper materials and adequate workforce, perhaps 18 standard." "Months," Velnara replied proudly. Zeftar's crystalline form chimed with what Jake recognized as disagreement. Velnara's design exceeds our parameters. We need a solution that can be implemented with available resources in available time. My analysis suggests we should request additional equipment from the Academy. That could take months, Jake pointed. Out. Better to wait for proper equipment than to attempt an impossible task, Zeftar replied. Quindal swirled faster in his suit. You are all thinking too small. If we could somehow modify the atmospheric conditions in this area, we could create updrafts strong enough to carry the equipment across. And how exactly would we modify planetary weather patterns? Throckman asked in his rumbling voice. Well, it would require significant research into local climate systems, Quindal admitted. Jake walked back to where his teammates were arguing. The sun was getting higher, and the heat was making everyone irritable. They had been discussing the same problems for 3 days now without getting any closer to a solution. He looked across the ravine again. 200 meters was a long way, but humans had been building bridges for thousands of years. His great-grandfather had been a construction worker who built bridges across rivers and canyons on Earth. His grandfather used to tell stories about how the old-timers would throw together temporary bridges with whatever materials they could find. Of course, those old bridges did not have to meet galactic engineering standards. They just had to work long enough to get the job done. What if we built something temporary, Jake suggested, just strong enough to get the equipment across once? His teammates looked at him with expressions ranging from confusion to horror. Temporary. Structures have unacceptable failure rates, Zeftar chimed. Without proper safety margins, the risk of catastrophic collapse approaches certainty. My people do not build temporary anything, Velnara clicked. A bridge is meant to serve for generations. Temporary solutions often become permanent problems, Throckman rumbled. Jake nodded and did not argue. He was learning that arguing with his teammates about philosophy was pointless. They each had thousands of years of species wisdom that told them their way was the right way. The problem was that their ways were not going to save those people in the 3 cities. As the day wore on, the arguments continued. Jake listened and asked questions and tried to understand each species' approach. But in the back of his mind, he was thinking about those old bridge-building stories his grandfather used to tell, stories about humans who found a way to get things done when everyone else said it was impossible. The second day started with more arguments. Jake crawled out of his simple human tent and found his alien teammates already deep in heated discussion about the best way to cross the ravine. None of them had slept well. The weight of their mission pressed down on everyone. Zeftar had worked through the night on his crystalline computing matrix. The device looked like a cluster of glowing gems that hummed softly as it processed information. He had run thousands of calculations and created detailed mathematical models that proved crossing the ravine was impossible with their current resources. Observe these stress calculations, Zeftar chimed, projecting holographic numbers into the air. Any structure built from available materials will fail when subjected to the weight of our equipment. The safety margin is negative 47%. Attempting such a crossing would be suicide. Jake studied the floating numbers. Zeftar's math was perfect, as always. The crystalline had calculated load factors, wind resistance, material strength, and dozens of other variables. According to pure mathematics, there was no way to build a bridge that would hold. Quindal floated above the ravine in his environmental suit, taking measurements with instruments that looked like metallic butterflies. His gaseous form swirled, with different colors as he worked. The nebulite had been studying wind patterns since before dawn. The atmospheric conditions are completely unsuitable, Quindal announced. Wind velocity varies by 30% within minutes. Cross currents create turbulence that would destroy any aerial transport system. Even if we could somehow lift the equipment, we could not control where it lands. Jake looked up at Quindal's instruments dancing in the air currents. The wind did seem unpredictable. Sometimes it was calm, Then suddenly gusts would sweep across the ravine strong enough to knock a person off their feet. Velnara had spread her 6 arms wide and was sketching detailed engineering diagrams on a large piece of metal sheeting she had carried from their supplies. Her drawings showed a magnificent bridge with graceful arches and decorative elements. Every joint was calculated for maximum strength and beauty. "This design will withstand any storm," Velnara clicked proudly. "The foundation anchors extend 60 meters into solid bedrock. The span utilizes triple redundant support cables made from crystallized carbon fiber. Construction time would be 14 months with a crew of 200 workers. Jake admired the elegant design. It would indeed last for centuries and could probably carry 1,000 times the weight of their equipment. It was also completely impossible to build with what they had. Throckman stood at the edge of his geological survey area, which now covered several square kilometers. His massive stone hands held instruments that could detect mineral deposits and rock formations deep underground. The Granite-born had been mapping alternative routes around the ravine. "I have located a path that avoids the ravine entirely," Throckman rumbled. "The route follows stable ground and has no significant obstacles. Total distance is 187 kilometers. Travel time would be approximately 53 standard days." Jake did some quick math in his head. 53 days would be too late to help the cities that needed earthquake prediction. But Throckman's route would be completely safe. No one would risk falling into the ravine or getting caught in equipment failures. While his teammates continued their discussions, Jake wandered away from the camp. He had spent yesterday listening to brilliant theoretical arguments. Today he wanted to look at the problem with his own eyes. He walked upstream along the ravine edge, noting how the gap changed width and depth. About 2 kilometers away, the ravine narrowed to roughly 150 meters. The cliff faces there looked more stable, with natural rock ledges that could serve as anchor points. Jake found an old mining trail that led down into the ravine. The miners had been gone for years, but they had left behind equipment and structures. Most of it was rusted and broken, but some pieces looked useful. Heavy cable, metal sheeting, support beams, and tools were scattered around abandoned work sites. He climbed back up and explored the area around their camp. A grove of bendwood trees grew about 1 kilometer away. These trees were native to the planet and were famous for being incredibly flexible. They could bend almost in half without breaking. Jake had read that early colonists used bendwood for construction projects that needed to move with wind or ground shifts. The more Jake explored, the more possibilities he saw. His teammates were brilliant, but they were thinking like their species always thought. Zeftar needed perfect calculations. Quindal wanted to control atmospheric conditions. Velnara required proper materials and construction crews. Throckman insisted on the safest possible route. Jake was thinking like a human. Humans had been solving impossible problems with whatever they could find for thousands of years. They built rafts from logs, bridges from ropes and planks, and shelters from whatever materials were available. The solutions were not always pretty or permanent, but they worked. He spent the afternoon gathering information while his teammates continued their debates. Jake measured distances, tested materials, and calculated loads in his head. He was not as precise as Zeftar's crystalline computer, but he had something his alien friends lacked. He had human intuition about what would work. By evening, Jake had a rough plan forming in his mind. It would not meet galactic engineering standards. It would make his teammates nervous, but it might just get their equipment across the ravine in time to save those cities. When Jake returned to camp, he found his teammates still arguing. The discussion had grown more heated as frustration built up. Each species was convinced their approach was correct, and the others were being unreasonably stubborn. "Your mathematical models ignore practical construction realities," Velnara was clicking at Zeftar. "You cannot build with pure theory. Your construction requirements exceed available resources by factors of hundreds," Zeftar chimed back. "Elegant design means nothing if it cannot be implemented." Both of you are ignoring atmospheric dynamics, Quindal swirled. Any structure must account for environmental forces or it will fail, regardless of theoretical strength. All of your solutions are unnecessarily risky, Throckman rumbled. The safe path may take longer, but it guarantees mission success. Jake listened to the familiar arguments while he prepared his evening meal. Each of his teammates was brilliant in their own way. Each had valid points about the challenges they faced. The problem was that their different approaches were completely incompatible. Zeftar's perfect calculations required materials they did not have. Velnara's beautiful designs needed construction resources that would take months to obtain. Quindal's atmospheric solutions required weather control technology that did not exist on this planet. Throckman's safe route would take too long to help the cities in danger. As night fell over their camp, Jake made his decision. While his teammates slept, he would try something that none of their species would approve of. He would build a bridge, the human way. It would not be pretty or permanent or mathematically perfect, but if he was right, it would work. Jake lay in his tent listening to the alien night sounds while his teammates settled into their various sleeping arrangements. Zeftar powered down his crystalline form with soft chiming sounds. Quindal sealed himself into his atmospheric rest chamber. Velnara folded her 6 legs and arms into a compact sleeping position. Throckmen simply stood still like a statue, which was how his people rested. When Jake was sure everyone was asleep, he quietly gathered his tools and slipped out into the darkness. The alien stars provided enough light to see by, and he had work to do. Jake moved quietly through the darkness, carrying his tools and portable fabrication equipment. The alien stars provided enough light for him to see where he was going. His teammates were all sleeping in their different ways, unaware that he had left the camp. He had spent 2 days listening to brilliant theoretical discussions about why crossing the ravine was impossible. Now he was going to prove that humans could find a way to make the impossible work. Jake had learned from his grandfather's stories that sometimes the best solution was the one you built with your own hands using whatever materials you could find. His first stop was the grove of bendwood trees he had discovered during his afternoon. Exploration. These trees were perfect for what he had in mind. They were strong but flexible, able to bend without breaking. Jake selected 6 of the straightest trees and began cutting them down with his fabrication laser. The laser worked quietly, slicing through the tough wood with a thin beam of concentrated energy. Each tree was about 20 meters long and as thick as his waist. The bendwood had a strange quality that made it stronger when it was under stress. The more force you applied, the harder it became to break. Jake loaded the trees onto his portable anti-gravity sled and moved to his next collection point. The abandoned mining sites in the ravine contained exactly what he needed: heavy steel cable that had been used to lower equipment into the deep excavations, metal mesh panels that had once covered dangerous areas, support brackets and joining hardware scattered around like metallic bones. The climb down into the ravine was dangerous in the darkness, but Jake moved carefully and tested each handhold before trusting his weight to it. His human balance and coordination served him well on the rough cliff face. Within 2 hours, he had salvaged enough cable and hardware to build what he had in mind. Back at the surface, Jake began the real work. His plan was simple in concept, but tricky in execution. He would build a suspension bridge using bendwood trees for the main support structure and steel cable for the suspension system. The walking surface would be metal mesh panels connected, with flexible joints. Jake started by positioning the bendwood trees as anchor points. Instead of trying to drive them deep into the rocky ground like traditional posts, he used their flexibility as an advantage. The trees would bend with wind and load forces instead of fighting them. This was completely opposite to how his alien teammates would approach the problem. Zeftar would want rigid mathematical precision in every connection. Velnara would insist on massive foundations and permanent attachments. Quindal would worry about wind loads destroying a flexible structure. Throckman would consider the whole approach too risky to attempt. But Jake was thinking like a human engineer. Humans had been building bridges for thousands of years before they had computers to calculate stress loads. They learned by trial and error, building structures that worked well enough to get the job done. If something broke, they fixed it. If the design had problems, they improved it. The suspension cable system was the most critical part of Jake's bridge. He used a technique his grandfather had described from the old days of bridge building on Earth. Instead of one massive cable that would be impossible to handle, Jake wove together multiple smaller cables in a pattern that distributed loads evenly across the entire span. Each individual cable was well within the strength limits of the salvaged mining equipment. But when woven together in the right pattern, they created a suspension system much stronger than the sum of its parts. The key was allowing each cable to stretch and adjust independently while still supporting the overall structure. Jake worked through the night, his hands remembering skills passed down through generations of human builders. He did not have Zeftar's mathematical precision, but he had something just as valuable. He had human intuition about how materials behaved under stress and how structures responded to real-world forces. The walking surface was perhaps the most innovative part of Jake's design. Instead of trying to create a rigid deck that would fight against the bridge's natural movement, he made a flexible surface that moved with the structure. The metal mesh panels were connected with joints that allowed each section to adjust independently. This approach would horrify his alien teammates, who preferred structures that behaved predictably. But Jake understood that flexibility could be a strength rather than a weakness. A bridge that could bend and twist with changing loads was often more stable than one that tried to resist all movement. As dawn approached, Jake was putting the finishing touches on his bridge. The structure looked nothing like the elegant designs his teammates had imagined. It was rough and improvised, built from salvaged materials and held together with creative engineering solutions that would not appear in any textbook. But it worked. Jake had tested each component as he built it, gradually loading the bridge with heavier and heavier weights. The bendwood trees bent and flexed exactly as he had hoped. The woven cable system distributed loads smoothly across the entire span. The flexible deck surface moved with the bridge's natural rhythm instead of fighting against it. The equipment transport system was Jake's final innovation. Instead of trying to carry everything across at once, he had designed a pulley system that could move loads one piece at a time. This meant the bridge never had to support more weight than it was designed for, while still allowing all the equipment to cross safely. Jake made 3 test crossings as the alien sun began to rise over the ravine. Each trip taught him something new about how his bridge behaved. The structure swayed and moved more than his teammates would like, but it felt solid and secure under his feet. The flexible design actually made it more comfortable to walk on than a rigid bridge would have been. The morning light revealed the full scope of what Jake had accomplished in a single night. His bridge stretched across the Kethmaran Ravine like a spider web made of wood and steel. It was not beautiful by galactic engineering standards, but it was functional and ready to use. Jake stood at the center of his bridge, looking back toward the camp where his teammates were probably just beginning to wake up. In a few minutes, they would discover what he had built while they slept. Their reactions would be interesting to observe. Zeftar would immediately begin calculating stress loads and failure probabilities. His mathematical mind would struggle to understand how a structure built without precise calculations could possibly work. Quindal would worry about wind loads and atmospheric effects on the flexible design. Velnara would be shocked that anyone would build a major structure without proper planning and materials. Throckman would consider the entire bridge an unacceptable risk, but Jake was confident his bridge would pass their tests. It might not meet their theoretical standards, but it would accomplish their mission. The equipment could cross safely, reaching the research station in time to help predict the earthquakes that threatened 3 cities. Jake heard voices from the direction of their camp. His teammates were beginning their day, probably preparing for another round of theoretical discussions about crossing the ravine. They had no idea that the problem had already been solved while they slept. He smiled and began walking back across, his bridge toward the camp. It was time to show his alien friends that sometimes the human way of doing things could work just as well as their more sophisticated approaches. Zeftar emerged from his crystalline shelter just as the morning sun painted the sky in shades of purple and gold. His form chimed softly as his systems powered up for another day of calculations and analysis. He was preparing to continue yesterday's mathematical discussions when something caught his optical sensors. There was a structure spanning the ravine. Zeftar's chiming became more rapid as his processing systems tried to make sense of what he was seeing. According to his calculations, building a bridge across the Kethmoran ravine was impossible with available resources. Yet there it was, swaying gently in the morning breeze like some impossible dream made real. "This cannot exist," Zeftar chimed, to himself, his crystalline form flashing with rapid calculations. His sensors focused on the bridge, measuring dimensions and analyzing materials. The structure appeared to be made from bendwood trees and salvaged mining equipment. Such materials could not possibly support the loads required for safe crossing. Quindal's environmental suit emerged from his atmospheric rest chamber, the gaseous being inside swirling with confusion and amazement. His instruments immediately began analyzing the bridge's interaction with local air currents. What he discovered challenged everything his species understood about structural engineering. The bridge is moving with the wind instead of resisting. Quindal announced through his suit's speakers. His gaseous form changed colors rapidly as he processed this information. Wind loads that should destroy any structure are actually making this one more stable. How is this possible? Velnara scuttled out of her shelter on her 6 legs, her multiple arms already reaching for measuring instruments. The arachnoid's compound eyes focused on the bridge with increasing astonishment. Her people were master builders who planned every detail before construction began. The idea of building first and calculating later went against thousands of years of architectural wisdom. This structure violates every principle of proper engineering, Velnara clicked, but her voice carried admiration rather than criticism. No foundation studies, no stress analysis, no construction permits, yet it appears to be functionally sound. I must examine the connection points immediately. Throckman's massive form rumbled as he processed what he was seeing. His people believed in careful planning and safe approaches to every problem. The bridge represented everything the Granite-born considered dangerous and irresponsible, yet it also represented a solution to their urgent mission. Who built this structure? Throckmen asked, though they all knew the answer. Only one member of their team would attempt something so audacious. Jake appeared at the far end of the bridge, walking calmly across the swaying structure as if it were a sidewalk on Earth. His human balance and coordination made the crossing look effortless. When he reached their side of the ravine, he found his 4 teammates staring at him with expressions ranging from shock to admiration. "Good morning," Jake said cheerfully. "I thought we could start testing the equipment transport system after." "Breakfast!" Zeftar's form chimed frantically as his calculation systems worked at maximum capacity. "Jake, my analysis indicates this structure should have collapsed under its own weight. The safety margins are completely inadequate by any reasonable engineering standard." Jake nodded and walked to the bridge's anchor point. "Your calculations assume the structure needs to be rigid. This bridge is designed to be flexible. Watch." He pushed against one of the bendwood support posts. Instead of standing firm like a traditional pillar, the tree bent gracefully and then returned to its original position. "The flexibility is the strength," Jake explained. "Instead of fighting against forces, the bridge moves with them. Wind loads get distributed across the entire structure instead of concentrating at weak points." Quindal floated closer to examine the bridge's response to air currents. His instruments showed readings that contradicted his species' understanding of atmospheric effects on structures. In high winds, most bridges become less stable. This design appears to become more stable as wind speed increases. That's right, Jake confirmed. The wind actually helps hold everything together. The more the bridge moves, the more the load gets spread out across all the support points. Velnara approached the bridge's construction joints with professional interest. Her 6 arms moved independently, testing connections and measuring tolerances. What she found amazed her engineering mind. These joints are crude by arachnoid standards, yet they serve their function perfectly. The imprecision actually adds to the structure's flexibility. Jake showed her how each connection was designed to move slightly under load. If everything was precisely fitted, the bridge would be too rigid. The loose tolerances let each part adjust to changing conditions. Throckman studied the bridge's foundation system with growing respect. Instead of massive concrete footings that would take months to build, Jake had used the natural flexibility of the bendwood trees as shock absorbers. This approach distributes foundation loads across a much wider area than traditional methods. Exactly, Jake said. Instead of concentrating all the force at specific points, the flexible foundation spreads it around. It's actually more stable than a rigid system in this kind of terrain. The testing phase began with Zeftar's insistence on precise load calculations. Jake demonstrated the modular transport system he had designed. Instead of carrying everything at once, equipment would cross one piece at a time using a pulley system that kept loads within safe limits. My calculations show maximum safe load for this bridge is approximately 200 kilograms, Zeftar announced after extensive analysis. That's perfect, Jake replied. Our heaviest equipment piece weighs 180 kilograms. The transport system breaks everything down into loads of 150 kilograms or less. Quindal conducted atmospheric stress tests, using his suit systems to create artificial wind currents that simulated storm conditions. To everyone's amazement, the bridge became more stable as wind speeds increased. The flexible design used air pressure to help support the structure instead of fighting against it. This contradicts everything my people know about wind engineering, Quindal admitted. Yet the test results are undeniable. Your bridge actually performs better in high winds than in calm conditions. Velnara's structural analysis was the most thorough. Her 6 arms probed every joint and connection point, while her compound eyes examined the weaving pattern of the suspension cables. The construction techniques are primitive by arachnoid standards, she concluded. But the functional engineering is brilliant. You have created emergent properties that exceed the capabilities of individual components. The most dramatic test came when Throckman volunteered to cross the bridge himself. His massive stone body represented the heaviest single load the structure would ever carry. As he stepped onto the flexible deck, the entire bridge adjusted to accommodate his weight. The bendwood trees bent further than they had for any previous load, but they did not break. The woven cable system redistributed Throckman's weight across dozens of individual support points. The flexible deck surface moved with his steps, instead of transmitting shock loads to the rest of the structure. The bridge feels solid beneath my feet, Throckman rumbled as he reached the center span. I expected unstable movement, but the flexibility actually provides better footing than rigid surfaces on uneven terrain. Jake watched his teammates' successful crossing with satisfaction. The bridge is designed to work with natural forces instead of fighting them. That makes it stronger and more stable than conventional designs. The equipment transport tests proceeded flawlessly. Each piece of delicate seismic monitoring equipment crossed the ravine safely, protected by Jake's cushioning system and the bridge's natural shock absorption. What the alien students had declared impossible the previous day was accomplished before the morning was half over. As the last piece of equipment reached the research station side of the ravine, Jake's teammates gathered around him with new respect for human engineering methods. They had learned something important about problem-solving that their species' traditional approaches had never taught them. Sometimes the best solution was not the most elegant or mathematically perfect. Sometimes The best solution was simply the one that worked when it was needed most. Professor Hicks Andros arrived at the Ravine crossing site 3 hours earlier than expected. The massive alien's multiple optical sensors immediately focused on the bridge spanning the Kethmaran Ravine. For several minutes, the professor stood, in complete silence, analyzing what should have been impossible. "Explain this structure," Professor Hicks Andros finally said, his voice carrying the authority of someone who had taught engineering for over 2 centuries. Jake stepped forward while his teammates gathered around. "We completed the equipment transport this morning, Professor. All seismic monitoring devices were delivered safely to the research station. They should be operational within 6 hours." The professor's optical sensors shifted to examine Jake more closely. "I asked you to explain the structure, not report on mission completion. How was this bridge constructed and by whom?" Zeftar's crystalline form chimed nervously. "Professor Jake built this bridge overnight using only locally available materials. My calculations indicated such construction was impossible, yet functional testing proves the structure is completely adequate for our mission requirements." Professor Hicks Andros moved closer to examine the bridge's anchor points. His sensors took detailed measurements of the bentwood tree foundations and the woven cable suspension system. These construction techniques do not appear in any galactic engineering database. What theoretical framework guided this design? Jake looked uncomfortable as all attention focused on him. "There wasn't really a theoretical framework, Professor. I just built something that would work with the materials I could find." "You constructed a major engineering project without theoretical analysis," the professor said. His tone was impossible to read. "You ignored standard safety protocols and proceeded without proper planning or approval." Velnara scuttled forward on her 6 legs. "Professor, I must report that Jake's construction methods were highly irregular. However, the functional results exceed expectations. The bridge successfully transported all equipment safely and efficiently." Quindal floated nearby in his environmental suit. "Professor, the bridge's interaction with atmospheric conditions defies conventional understanding. Wind loads that should destabilize the structure actually enhance its stability. I have never observed such counterintuitive engineering behavior." Throckman's massive form rumbled with what his teammates had learned was deep thought. "Professor, I initially considered Jake's approach dangerously irresponsible. However, testing proved the bridge safer than expected. The flexible design provides advantages that rigid structures cannot match." Professor Hicks Andros walked slowly across Jake's bridge, his sensors continuously recording structural behavior under load. The bridge swayed and flexed exactly as Jake had designed it to do. Instead of fighting the movement, the professor adapted his walking rhythm to match the structure's natural motion. At the center of the span, Professor Hicks Andros stopped and looked back toward the students. "This bridge represents a completely different approach to engineering problems. Traditional galactic methods emphasize theoretical perfection before implementation. This structure was clearly built using empirical iteration and practical adaptation." Jake joined the professor at the center of the bridge. "My grandfather used to tell stories about how humans built bridges on Earth. They started with what worked and improved it over time. They didn't wait for perfect solutions when people needed help. Your species' approach prioritizes immediate functionality over theoretical optimization," the professor observed. "This creates solutions that can be implemented quickly under resource constraints." "Yes, sir," Jake replied. "Sometimes good enough right now is better than perfect later." The professor's optical sensors focused on the equipment transport system Jake had designed. "Explain the load distribution methodology you employed." Jake demonstrated how the pulley system broke heavy loads into manageable segments. Instead of trying to make the bridge strong enough to carry everything at once, I made it possible to transport equipment in pieces that never exceed the structure's capacity. You modified the problem parameters instead of enhancing the solution capabilities, Professor Hixandros noted. This represents adaptive problem-solving rather than engineering optimization. The evaluation continued for another hour as the professor tested every aspect of Jake's bridge. He examined the flexible foundation system that used bendwood trees as shock absorbers. He analyzed the woven cable pattern that distributed loads across multiple support points. He studied the flexible deck system that moved with the bridge instead of transmitting stress loads. This structure violates numerous galactic engineering standards, the professor finally announced. Jake's teammates looked worried, but the professor continued. It also demonstrates engineering principles that our standards do not address: flexibility as strength, imprecision as adaptability, empirical iteration as design methodology. Professor Hixandros activated his communication system and began recording an official report. Mission summary. Student team successfully transported critical seismic monitoring equipment across Kethmoran Ravine using innovative bridge construction. Equipment delivery completed 67 hours ahead of projected schedule. All devices functional and operational. Jake's teammates relaxed as they realized the professor was pleased with their success. But Professor Hixandros was not finished with his evaluation. Student performance analysis. Crystalline student Zeftar provided excellent theoretical analysis that accurately identified design challenges. Nebulite student Quindal conducted thorough atmospheric studies that defined environmental constraints. Arachnoid student Vel Nara developed structurally sound designs appropriate for permanent construction. Granite-born student Throck Men identified safe alternative approaches that guaranteed mission success. The professor paused and looked directly at Jake. Human student Jake Morrison demonstrated problem-solving methodology unknown to current galactic engineering curriculum. Practical adaptation, resource improvisation, and empirical iteration produced functional solution when theoretical approaches failed to meet mission timeline. Professor Hixandros transmitted his report to the Galactic Engineering Academy administration. Within minutes, his communication system chimed with response messages from department heads across the galaxy. Word of the human students' bridge was spreading through academic networks faster than quantum communications. Jake, the professor, said, "I am recommending that your bridge construction methodology be added to our engineering curriculum. Future students need to understand that theoretical perfection is not always the optimal solution path." Zeftar's crystalline form chimed with what Jake recognized as excitement. "Professor, studying Jake's empirical methods could enhance crystalline, analytical capabilities. Mathematical optimization combined with practical iteration might produce superior results." Vel Nara clicked her agreement. Arachnoid construction techniques could benefit from human adaptive approaches. Flexible design principles might create structures that perform better under variable conditions. Quindal swirled enthusiastically in his environmental suit. Nebulite atmospheric engineering could incorporate human problem modification strategies. Instead of controlling environmental conditions, we could design systems that adapt to changing conditions. Even Throckmen rumbled his approval. Granite-born safety philosophy could expand to include calculated risks when time constraints demand immediate action. Conservative approaches remain important, but emergency situations may require human-style rapid solutions. As the day progressed, More professors and researchers arrived to study Jake's bridge. The structure became an impromptu classroom where different species could observe human engineering philosophy in action. Students took measurements, ran calculations, and conducted tests to understand how the bridge worked. Jake found himself explaining human problem-solving approaches to alien minds that had never encountered such methods. He described how humans built first and refined later, how they modified problems when direct solutions were impossible, and how they used available materials creatively instead of waiting for ideal resources. The bridge remained in place long after the equipment transport mission was complete. It became a symbol of cooperative learning between species and a reminder that there were many ways to solve engineering problems. Future students would study both traditional galactic methods and human adaptive techniques. Jake's teammates gained new respect for human capabilities and new understanding of their own species' strengths and limitations. They learned that combining different approaches often produced better results than any single methodology could achieve alone. The Keth Morin Ravine Bridge entered Academy history as the first structure built using human empirical engineering methods. More importantly, it became a bridge between different ways of thinking about problems and solutions. Jake Morrison returned to his studies with a new appreciation for what humans could contribute to galactic civilization. His overnight construction project had become more than just a successful mission. It had become a lesson in the value of diversity in problem-solving approaches and the importance of practical solutions when theoretical perfection was not possible.